Now that's the standard Riemann integration theory, but another way that one can introduce Riemann integration is via Riemann sums, where we don't necessarily take a max or a min, but we evaluate at some point inside the interval. This gives us more flexibility, but it also means that we have to consider more objects, and so that's why it's nicer to develop the theory in terms of maximums and minimums and upper Riemann sums and lower Riemann sums. But we can also relate it to general Riemann sums. But now we have to expand upon our definition of what we mean by a partition. So let A and B be real numbers with A strictly less than B, and F on the interval AB into R bounded. A marked partition of AB, and we'll call it P star, is a pair P TK, K equals 1 to N, where P equal x0, x1 up to xn is a standard partition of AB, and TK in the set lives in xk minus 1 xk for all k equals 1 up to n. And so in particular, these TKs indicate where we're marking each interval. And that mark indicates where we want to evaluate the function to construct a Riemann sum. And whenever we have this, again, we'll set delta xk to be equal to, again, xk minus 1. And we still have a notion of the norm of P star. So the norm of P star now, well, we just inherit the norm from just P. So these TKs ultimately don't matter for that norm. Of course, when we have continuous function, we can use the extreme value theorem to pick out the right TKs so that we can get the upper Riemann sums or lower Riemann sums. But in general, if you don't have continuity, you can't guarantee that. Now, a Riemann sum of F with respect to the marked partition P star is S F P star equal sum k equals 1 to n. I evaluate f at tk, and I multiply by delta xk's. Now that's a general Riemann sum. We've seen the upper Riemann sum, lower Riemann sum. This is the general one. And then we say that the Riemann sums converge to, we'll call it I of f. So now we have a bunch of symbols floating around. So we have the s integral of f, and now we have just I of f to integrate. And so right now we don't know that these quantities are equal, and that's why we need to distinguish them symbolically. As norm p star goes to 0, if and only if given epsilon greater than 0, there is a partition p epsilon of a, b, such that if q star is a marked partition, such that q is a refinement of p epsilon, then I can ensure that SF, the Riemann sum with respect to this refined marked partition, minus IF is less than epsilon. And we write I of f is equal to the limit as norm p star goes to 0, s of f p star is equal to the limit as norm p approaches 0 sum f of tk delta xk. So we notice that the markings ultimately don't matter. They kind of universally have to align so that you eventually obtain quantities close to the integral. Now, of course, in textbooks you'll see that they'll set delta x goes to 0, and that delta x is typically defined to be the maximum of the delta xk's, which in this case coincides with our norm of the partition. So it's just slightly different notation for exactly the same quantity. But you could reasonably write delta x goes to 0, and no one would really complain. Again, we need to establish that our notion of integration coincides. So basically we have two notions of integration right now. We have in terms of upper and lower Riemann sums being closer and closer to each other. We have things in terms of the upper Riemann integral and lower Riemann integral equaling each other. Those are equivalent, and now we'll show that f a, b into r is Riemann integrable if and only if the Riemann sums of f converge to this quantity IF, a real number, on AB. In this case, IF is equal to this integral, a to b, f of x dx. We've seen that if it's Riemann integrable, then this quantity is well defined, and now we have a way of establishing that whatever this limit, or in the sense of this limit, is, it has to be equal to this integral. To prove this theorem, we first suppose that f is Riemann integrable and proceed to show that f converges to I of f, which is equal to this integral, of course, on AB. So suppose f is Riemann integrable. By our previous theorem, this means that the upper Riemann integral is equal to the lower Riemann integral. And the approximation property of suprema and infima, for that matter, provides us with partitions which we will denote S and T of AB with the integral a to b f of x dx minus epsilon less than L of f on the partition S, and we also get an upper bound in terms of this T partition for a fixed epsilon greater than 0, of course. So now we're going to say that we can set P epsilon equal to simply the union of those partitions. And now we endeavor to show that when we take a refinement of P epsilon and mark it, then we get the desired inequality. Note that if Q is a refinement of P epsilon and Q star is a marked version of Q, then we'll have to have that the integral from a to b of f of x dx minus epsilon, well, that's going to be less than L of f s, which is less than or equal to L of f P epsilon because it's a refinement. But when I have a refinement of P epsilon and I mark it, I'm guaranteed that I'm going to bound this number by the corresponding Riemann sum. In particular, this is always going to be a function that's strictly dominated by the function associated with the constant approximation via this marked partition Q star. But in turn, this quantity is going to be less than the upper Riemann sum on P epsilon, which is of course less than T upper sum, since P epsilon is a refinement. And then on this side, I'm going to get A, B. And then on this side, I'm going to get the integral A, B, f of x dx plus epsilon. Now when we put this all together, ultimately this will imply when we subtract this integral from both sides of this and this middle part here, which is the Riemann sum, and hence now this worked for any refinement and marking extending from P epsilon, and this worked for any epsilon, and this quantity was fixed, and therefore we conclude that the Riemann sums converge we conclude that the Riemann sums converge. Now, assume that the Riemann sums converge. So now we're trying to prove the converse. So since the Riemann sums converge, let epsilon be greater than 0 and acquire P epsilon over 4, which will still be greater than 0, with S F Q star minus I of F less than epsilon over 4 for any marked refinement Q star of P epsilon over 4. And for now, we'll just let this be denoted by P to simplify our argument. We also note that epsilon over 4b minus a is greater than 0. So by the approximation properties, there are tk and sk such that tk, sk are in the interval xk minus 1, xk, where of course these are the xk's from my partition, with, of course, I want to have a close approximation to the largest value of f. Of course, I can't get my hands on a point where it's equal necessarily because I haven't assumed continuity, so I can't invoke the extreme value theorem. But I can say that I've got this less than epsilon over 4 times b minus a, and f of sk minus little m kf less than epsilon over 4 times b minus a as well. Letting p star 1 be the marked partition on P with the tk points that I found, and P2 is defined similarly, but with the SKs. We have that U FP minus S F P1 star will be equal to, well, I sum k equals 1 to n mk of f minus f of tk delta xk. And by this this bound, I know that this is less than, I'll get an epsilon over 4 b minus a, but when I sum this in telescope, I'm going to get a b minus a factor, and so ultimately this will be bounded by epsilon over 4. And similarly, S F P2 star minus L F P is, again, by a very similar calculation, less than epsilon 4. So now putting this together, we'll have that U of Fp minus L Fp well, basically, I'm going to add these two inequalities together and then bring the s terms over the other side, and that'll give me less than epsilon over 4 plus S F P1 star. And then I'll, of course, have a subtraction here, so I've got plus epsilon over 4 minus S F P2 star, which is, of course, less than or equal to, I add up the epsilon terms, and then I take the absolute value of this difference, S of F P1 star minus S of F P2 star. Now, sneaking in I of F, that is adding and subtracting I of F inside of this absolute value, I can apply the triangle inequality to get that this is less than epsilon over 2 plus SF P1 star minus I of F plus S F P2 star minus I of F. But note that these are trivially refinements of P and refinements which I've marked. And in particular, that P is P epsilon over 4, and so I'm guaranteed that this is less than epsilon over 2 plus epsilon over 4 plus epsilon over 4, which then gives me epsilon. With a very small amount of additional work, we can guarantee that the upper and lower limits are in fact equal to this I of F. That is the upper integral and lower integral, so be the I of F. And therefore we also obtain the formula. Now we're going to establish the fact that the integral enjoys a lot of nice properties. So this is proposition, not property. Suppose F is Riemann integrable on AB. Then F is also Riemann integrable on AC and CB for any C inside the interval AB, and the integral AB f of x dx is actually equal to the integral from A to C f of x dx plus integral from C to B f of x dx. So we'll actually prove the formula by proving integrability in a particular way. So let C be in AB. Well, we're going to show things in terms of upper Riemann integrals and lower Riemann integrals. And in particular, let U AC of F and L AC of F denote the upper and lower Riemann integrals of F on AC respectively. And similarly, we can define this for any other interval, for example, CB. And we'll let U of F simply denote the usual integral from A to B, and L of F be similar. Now those quantities are equal since I have that this thing is Riemann integrable, and I can employ that theorem. So now let Q1 equal x naught up to xn, and Q2 equal y1 up to yn, well, ym, say. We want it to be arbitrary. be partitions of AC and CB, respectively. And define the partition Q of AB by Q is equal to x naught all the way up to xn, and then the next element is going to be y1. And the reason we can do this is because y naught and xn are both equal to c, since they're partitions of these intervals with these endpoints c. And I go all the way up to ym. And due to this decomposition, we note that. So we have that the upper Riemann sum of the function f with respect to the partition Q is going to be equal to the sum k equals 1 to n of mk, but now we have to be a little careful because these are in terms of the x's. And so let's denote that these are the x's from the Q1 partition of f, delta x, k. And then I also get the next part of the sum because these overlap. So in particular, this xn having y1 minus xn will give me delta y1 back again, and evaluating on this interval is the same as evaluating mk with respect to the partition Q2 f delta yk. But when I look at these, I realize that these are just the upper sums with respect to the interval AC with respect to the partition Q1 plus the upper sum over the interval CB of F with respect to the partition Q2. Now we get two things from this procedure. The first thing we note is that this is greater than UAC of F, because this is the infima over such Q1, and this is similarly the infima over such Q2. So I have that this quantity is greater than or equal to always. On the other hand, any partition P I can always refine into a Q that decomposes in this manner, and therefore I'm going to have that the infimum is always bounded by this quantity, and therefore U of F will be greater than or equal to U AC of F plus U CB of F. In the other direction, we're going to have that this has to be greater than or equal to U of F, and so I've got U of F must be less than or equal to UAC FQ1 plus UCD FQ2. And since this holds independently for each Q1 and Q2, and Q1 and Q2 are independent of each other, I can take the infima of both of these quantities, and I'll still have the lower bound U of F. So U of F must also be less than or equal to U AC F plus U CB F. Thus, U of F is equal to U A C F plus U C B F. And I have that at least the upper Riemann integrals decompose in the way that I would like. However, a very similar, almost exact reasoning, but with supremums instead of infimums, leads us to conclude that L of F is actually equal to LAC of F plus LCB of F. And now here's what we do. By way of contradiction, suppose UAC of F is strictly greater than LAC of F. And similarly, by symmetry, we could do the same thing with UCB, and we'll arrive at a very similar contradiction. So this is, without loss of generality, something that we can assume by way of contradiction. That is, these integrals don't coincide. Then UCB of F is less than UAC. That is, I'm going to add the difference between these. Now I've shown that the lower Riemann sum satisfies this equality, and the upper Riemann sum satisfies the above equality. And since L of F is equal to U of F by assumption, we're going to have that this entire quantity is actually equal to L of CB of F. And therefore I have the upper sum, or upper Riemann integral, strictly less than the lower Riemann integral, which is of course false. And therefore we conclude that U CB F is equal to L CB F, and U AC F is equal to L AC F, and the result follows.